I welcome you all in today's NPTEL online certification course lecture on mechatronics. Today we are going to talk about the digital circuits. It's a second lecture basically. So, here basically what I will be talking about is that how to convert a truth table into a Boolean expression, and also the various type of memory devices such as flip flops. Okay. So, various versions of it that I am going to talk about in this lecture. So, basically we are here in the this particular portion, that is the digital control architecture of the mechatronic system components. And in the last lecture we have seen various type of gates. Okay. And here as I said, we are going to find out a Boolean expression given a truth table. Okay. So, there are two approaches which are used. One is the sum of the product approach, okay, and other is the product of sum approach basically. Okay. So, in the sum of the product approach, here the output is represented as sum of the product containing the combinations of the input. Okay. So, suppose we have here the two gates here, the two AND gates basically, okay, and here these two AND gates output are connected to a OR gate. Okay. So, input say for the first one is A and B. So, the output of that is A dot B. Similarly, for the second AND gate, the inputs are A and C. So, the output is A dot C, and when these two are passed as input to the OR gate, we get output say X as AB plus AC. Okay. So, here as I said, if we have inputs A, B and C and output X, the sum of the product would be A into B plus A into C. The second method is what we call it as the product of sums method. Okay. So, here basically the inputs are given to the two OR gates, okay, here, and these output of the two OR gates are given as input to a AND gate. Okay. So, as you can see here, A and B are the input to the say first OR gate, okay, and so the output is going to be A plus B, and for the second OR gate the inputs are A and C. So, the output is going to be A plus C, and when these two are sent as an input to a AND gate, what we get is as A plus B into A plus C. So, it represents output as a product of sum containing combinations of the input. Okay. So, this is what I just talked to you. Now, I can give an example. Suppose I have been given a truth table, okay, and I am asked to write a Boolean expression for that. So, let us take an example. Say you have the three inputs A, B, C, and you have a output like this. Okay. So, the process is that what we do is that we write expressions for row having non-zero output. Okay. So, for example, non-zero outputs are there in these two rows. So, the expression for this in the product form that is through AND gate can be written as say A invert, B invert and C invert. Okay. And when you take a product of that, you will be getting output as 1. Similarly, here you see that we have input 0 and 1 and 0. So, for 0 for A and C which has input 0, we take the invert like this, okay, and we have the B which is already 1. So, B is written as it is. So, the first step is that sum the expression of the non-zero rows, okay, and the sum of the products can be expressed here as you can see that A invert, B invert plus C invert plus A invert B and C invert. I can take A invert and C invert out. So, I get B invert plus B and which is basically going to be equal to A invert C invert. So, this way I can convert this truth table into this Boolean expression. Next, let us look at the sequential logic. Okay. So, the combinational logic system which we have seen in the previous lecture, the output is determined by the combination of the input variables at a particular instant of time. Okay. So, that we have seen, in fact, I have taken an example also. Okay. So, that we have already seen. Now, when a system requires an output which depends on the earlier values of the input, okay, a sequential logic system is required. Okay. So, in this case basically since the output is depending on the earlier values of the input, we require a certain type of memory device. Okay. That means that the sequential logic system requires a memory. So, basically we have a combinational logic system here, and if this has a memory, okay, a device is also there. So, the input from the memory device basically, okay, this will be leading to the sequential logic system and you will be having the output from here. Now, sequential logic devices usually responds to input when a separate trigger signal transitions from one level to another level, okay, and this trigger signal we usually call it as a clock signal, okay, or represented in short CK, that is a clock signal. The clock signal can be a periodic square wave or an a periodic collection of pulses, okay, and these clock pulses could be a positive edge when it goes from 0 to 1 or low to high, or it could be a negative edge when it goes from 1 to 0. Okay. So, that is there. So, it could be this way or it could be this way. So, the positive edge triggered devices responds to low to high, that is 0 to 1 transition, whereas negative edge trigger devices respond to high to low, that is 1 to 0 transition. Okay. And devices in this class include say flip flops, counter, monostables, latches and more complex devices such as microprocessors. Now, let us look at the flip flop. Okay. The flip flop is a as I discussed just now, the sequential logic device used for storing and switching between the two binary states to store the digital data in the form of bits as demanded by say digital memory devices such as computer RAM. Okay. Also known as bistable device because it has two and only two possible stable output states, that is high and low. It has the capability to remain in a particular output state, okay, until input signal causes it to change the state. So, as I said, it is a basic memory element which is made up of logic gates, okay, and there are number of forms say SR, that is set, reset, flip flop involving the NOR gates. Okay. So, here we can say that we have the NOR gate say A and NOR gate B. From here is the set input and from here is the reset input. Okay. And the other input to these gates are output of the other gate. Okay. So, for example, input if these outputs are Q and Q bar. Okay. So, the input for A is going to be the Q bar and similarly input for B is going to be the Q. Now, initially say Q is equal to 0, Q bar is 0, S is equal to 0 and R is equal to 0. Okay. Next say if we have S is equal to 1. Okay. So, if 1 this is 1, so and this is 0. So, you are going to OR gate output is going to be 1 and invert is going to be 0. Okay. So, the Q bar will be going to be 0. So, both input to the NOR gate A are 0. Okay. So, this is already 0 and this Q bar is 0. So, here the NOR gate A output is going to be 1. So, you have Q is equal to 1. Now, both input to the NOR gate B are 1. Okay. So, this was already 1 and now this is 1. Okay. So, you have both as 1. So, the NOR gate output is going to be 0. So, you have the Q bar is equal to 0 and no more changes. So, there is no more change by putting S is equal to 1. Next say what I am doing is that I am putting S is equal to 0. Okay. Now, if this is 0 and so this was 1. Okay. So, again this invert is going to be 0. So, I have dot Q bar is equal to 0. So, there is no change in the output state of Q bar even when S changes from 1 to 0. Okay. So, what does this mean? This means that it remembers the state it was set to. Okay. It remembers the state it was set to. Now, suppose what we do, we change R from 0 to 1. Okay, and when S is equal to 0. Okay, previous case we have taken S is equal to 0. So, when S is equal to 0, suppose I am changing R from 0 to 1. Okay, what we have is that the output from NOR gate A changes to 0. Okay. So, 1 and 0, so its output is going to be 0. So, the output from NOR gate A changes to 0 and the output of NOR gate B changes to 1 because the 0 0 and its invert is going to be 1. Okay. So, the flip flop has been reset. Okay. So, this is what it means that when you change the R to 1, the flip flop has been reset as your Q bar is being going to change to 1. So, schematic representation of RS flip flop is as here you can see that you have set, reset and input output Q and here you have the Q bar. Okay. So, here S is the set input, R is the reset input, Q and Q bar are what they are called at complementary outputs. Okay. Most of flip flop include both outputs where one output is in the inverse of the other. So, I can summarize. Okay, the RS flip flop operates on the following rules basically. As long as the input S and R both are 0, the outputs of the flip flop remain unchanged. Okay, and when set is 1 and R is 0, the flip flop is set to Q is equal to 1 and Q bar is equal to 0, and when S is 0 and R is 1, the flip flop is reset to Q is equal to 0 and Q bar is equal to 1, okay, and it is not allowed to place as 1 on both S and R simultaneously, since the output will not be predictable in that case. Okay. So, here basically we have say at S 0 0 we have some initial values, okay, and with 1 0 this is 1 0, and with 0 1 this is 0 1, and 1 1 this is not defined, not allowed. Then triggering of the flip flop. Okay. So, when should this change from change of input from S to R is to be done? Okay. This is what we call as the triggering. Okay. So, flip flops are usually clocked, that is a signal designated clock coordinates or synchronizes the change of the output states of the device. This allows the design of the complex circuit such as a microprocessor when all system changes are triggered by a common clock signal. Okay. And this is what is called as the synchronous operation, because the change in states are coordinated by the clock pulses. Now, the output of different types of clock flip flop can change on either a positive edge or a negative edge of a clock pulse. These flip flops are termed as the edge triggered flip flops, okay, and the positive edge triggering is indicated schematically by a small and angle bracket on the clock input to the flip flop, and the negative edge triggering is indicated simultaneously by a small circle and angle bracket on the clock input. So, this is here how we represent the negative edge triggered one, and this is how we represent the positive edge triggered RS flip flop, okay, and the positive edge triggered RS flip flop truth table is going to be this one, as I discussed with you. Now, the up arrow here in the clock column represents the positive edge transition from 0 to 1, and the N arrow indicates, as I said, the input condition that row is not allowed. Okay. So, as long as there is no positive edge transition, the values of S and R have no effect on the output as shown by symbol X in the last row of the table. An example timing diagram is shown here below. Okay. So, the output is reset, that is Q is equal to 0, okay, at the first positive edge, okay, at the first positive edge of the clock signal. Okay. So, where R is equal to 1 and S is equal to 0. Okay, and at the output is set Q is equal to 1 at the second positive edge where S is equal to 1 and R is equal to 0. Okay. So, that can be seen here. Okay. So, here you can see that at this location the Q value is 0, okay, and here R is equal to 1 and S is equal to 0, and you have the clock signal over here. Okay. Similarly, we can see that the Q value is 1 say over here at the second positive edge, that is at this place, okay, where S is equal to 1, okay, and R is equal to 0 in this zone. There are special devices that are not edge triggered, okay, and an important example in this is what we call it as a latch. Okay. Now, the output Q tracks the input D as long as clock is high. Okay. And when a negative edge occurs, that is when the clock goes low, the flip flop will store the value that the D had at the negative edge, and that value will be retained by the output. Okay. So, that is there, and because the output follows the input, when the clock is high, we say that the latch is transparent during this time. Okay. So, you can see that you have 0 1 here and you have 0 1 here. Okay. And so, here when this is 0, this is 0, and when this is 1, this is 1, and these are the clock. Okay. So, so this is there. Okay. And this is the latch, this is the clock, you have output Q bar, and this is the input signal. Okay. So, here we can see that the output Q tracks the input D while the clock level is high. Okay. That is Ck is equal to 1. Okay. So, when the Ck is equal to 1, your output here tracks the input. Okay. So, that is there. The X in the last row of the table indicates that the values of D has no effect on the input as long as Ck is low. Next, let us look at isochronous inputs. Okay. That is one which is not clocked. Okay. So, flip flop they are not triggered by a clock signal. Okay. Okay. So, flip flop may have say preset and clear functions that instantaneously overrides any other input. They are called asynchronous input because their effect may be asserted at any time, and as I said, they are not triggered by a clock signal. Okay. So, the preset input is used to set or initialize the output Q of the flip flop to high, and a clear input, okay, is used to clear or reset the output of the flip flop to a low. Okay. So, here we have say a D flip flop. Okay. The D flip flop, also called a data flip flop, has a single input D whose value is stored and presented at the output Q at the edge of a clock pulse. A positive edge triggered D flip flop is shown over here. Now, unlike a latch, the D flip flop does not exhibit transparency. Okay. So, the output changes only when triggered by the appropriate clock edges. Okay. So, that is how it is. Okay. And here is the truth table for the D flip flop. Next, let us look at the JK flip flop. The JK flip flop is very similar to the RS flip flop which we have seen, where J is analogous to the set input and K is analogous to the R or the reset input. Now, the major difference is that the J and K inputs may both be high simultaneously. We have seen that in case of RS flip flop, the R and S value both 1 were not allowed. Okay. But in case of JK flip flop, okay, these values may be high simultaneously, that is both the J and K values can be 1 together. Okay. And this state causes the output to toggle, which means that the output changes values, that is 1 would become 0 and 0 will become 1. So, this is how JK flip flop looks like. You have a preset terminal, clear terminal, JK, and here is the clock. So, you have output Q and Q bar, and this table actually explains you the truth table of a negative edge triggered JK flip flop. Now, here the first 2 row of the table describes the preset or clear function, that can be used to initialize the output of the flip flop, and the third row precludes presetting and clearing simultaneously, and the down arrow actually represents the negative edge of the clock signal, which causes the change in the output. Okay. And the last row describes the memory feature of the flip flop in the absence of a negative edge. Now, coming back to application of flip flop, okay, so these flip flops can be used for situations such as switch debouncing, which is very useful, okay. Then data register, binary counter and frequency divider, serial and parallel interfaces, okay, and bounce elimination switch, data storage, data transfer and latch. There are special purpose digital integrated circuit for such as decade counter, ischemic trigger and 555 555 timer ICs. Okay. So, we will just discuss very brief about this. So, the decade counter is like flip flop circuit. Decade counter is another common counter which can be used to perform the binary counting. Okay. It is a negative edge triggered counter. The output is a binary coded decimal, that is BCD, consisting of 4 bits, making it useful for decimal counting application. And the binary coded decimal counters can be cascaded to count in power of tens, okay. And cascading the 2 BCDs raise the range for counting down from 0 to 99, and further cascading allows the counting of higher powers of 10. So, a convenient device for viewing a BCD output is a 7 segment display driven by say 7447 BCD to 7 segment decoder. The details about this I have discussed in my another lecture on the display. Ischemic trigger is the device that can convert say a noisy or jumpy fashion signal into a sharp pulse using the threshold hysteresis effect. So, you can see that these noisy or signal can be converted into a sharp square pulses. Okay. The output goes high when the input exceeds the high threshold and remains high until the input falls below the low threshold, that we can see from the figure. The hysteresis between the low and high threshold result in the distinct edges in the output. Okay. And the 6 ischemic triggers are usually packaged on a single IC, okay. And for example, 7414 a hex ischemic trigger inverter. Now, let us look at the 555 timer. Okay. The 555 IC is known as the time machine because it performs a wide varieties of timing tasks, okay, and it is a combination of digital and analog circuit. So, you are here seeing the 2 type of packaging basically, okay. So, that is there, FK package is there, and this is the 555 pin out. Application of this 555 includes bounce free switches, cascade timers, frequency dividers, voltage control oscillators, pulse generator and LED flashers. Coming back to the logic gates, logic gates find very wide application in basically these 3 purpose. One is the parity generator. What is parity? I am going to talk about, and the digital comparators we have seen mostly used in the feedback circuits, and the code converter, okay, that is for the conversion of code from one system to another one. Okay. So, as I said, parity generator. So, first of all, let us see what is a parity basically. Okay. So, when the data is transmitted, because of noise in the transmission, it may happen that one may be received at 0 or the say the vice versa, 0 may be received as 1. So, to overcome this, an extra bit is added and this may be 0 or 1 and what we call it as the parity bit. Okay. Next is the digital comparator, okay. And so, this extra bit is added in the parity bit, and then what we do actually by adding, then we count actually basically that in the input side how many ones were there and in the output side whether the same number of ones are there or not, okay. So, that is how we ensure that the same data has been transmitted. Next is the digital comparator. A digital comparator is used to compare two digital words to determine if they are exactly equal, okay. And the two words are compared bit by bit and a one output is given if words are equal, okay. To compare the equality of two bits, an XOR or exclusive OR gate can be used. Digital comparators are available as ICs and can generally determine not only if the words are equal, but which one is greater than the other, that can also be found out by the digital comparator. Next, let us look at the code converter, and as I said, this is used to change data from one type of code to another type. Okay. For example, the output from a microprocessor system might be a BCD, okay, that is binary coded decimal, and this need to be transformed into a suitable code to drive say a 7 segment display. Okay. So, the data decoding is used for the process of converting some code group, that is say BCD, binary, hex into an individual active output representing that group. Okay. A 3 line to 8 line decoder is used where a decoder has 3 input line and 8 output lines. Okay. So, these are the references if you wish to read further about the digital logics, digital devices, okay, the combinational as well as the sequential one. Okay. You can go through these books. Thank you.